everyone. Hopefully you can hear me. We've been having some technical difficulties with the sound and ran out of time for doing further tests, but hopefully you can hear me. Let me know in the chat if you can hear me okay. And let's see how this goes. And if so, we will get started with week 7. Just waiting to see if everyone can hear me at all or not. There's a lot of noise, static noise, and distortion. Okay, give me 1 second. Okay, let's see if this is a bit better. I'd appreciate it if you let me know if this is working a bit better. Hopefully everything is working better now. Unfortunately, I don't know that I can make any other improvements to the sound. I'm not sure exactly why. Much better now. Oh, phew. Excellent. Let's get started. That is good news. Fantastic. Thank you for your patience. This is week 7 of the 17th semester of the Massive Open Online course for the University of Nicosia's master's degree in digital currencies. And let's get started. This session is about classification of tokens. I see you in the chat. As you can hear me, we're all ready to get started. Try to keep your questions on point and relevant to today's conversation. I am still, unfortunately, suffering a bit from COVID, 2 weeks from when I first got symptoms. So I occasionally cough. If I do, I'll try to mute myself and not cough in your ears. So cheers to that. I have to drink a bit of tea. Okay. Our first question comes from Dennis. Dennis is asking about classification of other major coins and tokens. How would these major coins, tokens be classified? They're not explicitly mentioned in week 7 slides. Yeah, because really in the slides, what we try to do is give you some examples that are good examples for each category. There are literally thousands of different cryptocurrencies, platform currencies, stablecoins, etc., etc. We can't possibly cover all of them. We can't even cover the top 20. So the first question was about Ripple XRP. I would classify Ripple XRP as a cryptocurrency. That seems fairly specific to me. It's my characterization as a cryptocurrency would be it's not a platform. You don't run smart contracts on it or other types of smart apps. And it's primarily intended as a bank-to-bank protocol, perhaps. So that would be that. Corda, I would consider a platform. Solana is a platform. Clearly, it's for smart contracts. Dogecoin and Shiba Inu, You can either consider them cryptocurrencies or collectibles. What they really are is cryptocurrencies that only have the purpose of being a collectible because they have no serious use. So since we don't have a category for joke currencies, I really call them cryptocurrencies. All right. Then we have some similar questions about Cardano, ADA. Patrick asks, articles I have read about Cardano tend to fall into two camps. One stating that it is simply an Ethereum clone, whereas others see it as being able to carve out a successful niche, pointing to its acceptance by regulators in Japan and adoption in Ethiopia. I'm interested in enlisting your opinion, its use cases, and future viability. I don't have an opinion. And generally speaking, I don't really have an opinion on future viability of any system in this space, perhaps with the exception of Bitcoin, only because that has kind of shown viability over a very long period of time. And I only have comments on use cases for a handful of cryptocurrencies and platforms. I tend to have a personal opinion on these issues, which isn't really relevant to the topic of today. See, the thing here is that, quite honestly, you should not be seeking opinions and analysis by so-called influencers and self-proclaimed experts, or even those who are teaching you a course like this. Because that's not how this technology works. I can tell you all about the technology if you want, but if you are interested in use cases and future viability, that's not really something that can be objectively analyzed. Use cases are up to the users, and future viability is a guessing game. I think what's really important to take away from these courses is to equip yourselves with the tools that you can do your own analysis. And I don't want to mean the try to do your own research cry that you hear from people who don't know how to do research and have never done research. Really make your own opinion, which will be subjective and possibly most likely biased in many ways, but try to clarify why you arrive at certain conclusions by setting out the criteria that you will use to analyze something, and then trying to be consistent in how you analyze different things in order to decide if you want to be interested in research further or get involved in any of these technology platforms. I think that's the real key here. Our next question comes from Andreas, my namesake. Andreas asks, what is the incentive for the issuer of a stablecoin to issue, maintain, and secure the stablecoin? Do stablecoins usually have a concept of mining and/or fees? This is an excellent question. Stablecoins do not generally have mining, but they do have fees. They have transaction fees. And in many cases, those transaction fees generate enormous amounts of money for the people involved in stablecoins. Second to that, when you have a stablecoin that is based on some kind of reserve asset, like, for example, holding US dollars in a bank account, even the most basic of savings account will generate some interest, and as interest rates go up, more than that. And obviously these stablecoin companies may invest the reserves in various things, which isn't wise and is incredibly risky, because you don't do that with the reserves that you have for a pegged asset, but they will. And they'll do it because they can get away with it. It's mostly an unregulated industry. So as a result, they can make quite a bit of money, even if they just put it in something boring like bonds, U.S. Treasuries or something like that. So stablecoins are actually very, very profitable for the companies that have them, just like banking is. And in many ways, it's very similar to banking. You put money into stablecoins. That means that money is deposited in accounts, and that capital that's sitting there can be used to generate loans, to be used for some low interest investments, or whatever else they might do with it. Swapan has a similar question about stablecoins. Do stablecoins have intrinsic value, or are they backed 100% by fiat currencies? Well, it depends on the stablecoin, but stablecoins don't have intrinsic value. Generally speaking, I'm very reluctant to use the term intrinsic value. Obviously, I'm not an economist. I'm going to give you some opinions based on a layperson's understanding of the economics and its relation to the technology. I'm a computer scientist. But to me, intrinsic value has never made sense. There's nothing intrinsic about value. Value is very much extrinsic. It's not in of the thing itself. It is something that we give something because we give it value because it has value to us. It's a subjective thing, and it has a lot to do with scarcity and use, utility and scarcity. So do stablecoins have intrinsic value? No, probably because nothing has intrinsic value. But do they have value outside of the reserves that are held? And again, that really depends. But I would say probably not, unless they have some utility and at the same time some other characteristics that give them scarcity or unique characteristics of utility that are not available in other stablecoins. I would say that their value is essentially whatever reserve fiat currency they have behind them. And the value of that fiat currency is simply the economic activity that happens in the broader economy. Generally speaking, stablecoins don't have enough economic activity to have their own value, absent of the reserves. All right, we have some follow-up questions. Everybody wants opinions on different cryptocurrencies, platforms, stablecoins, etc. I'm not really going to give you an analysis or opinion on any one of these things. Hassan asks, in privacy coins, if it's hard to trace transactions, what prevents users from spending the same amount twice? That is a great question. So the reason it is users are prevented from spending the same amount twice is because of a technology used within Monero and most other systems that are similar, known as a zero-knowledge proof. A zero-knowledge proof is where you prove something without revealing any knowledge about it. So for example, in a transaction, you can prove a specific range proof, as it's known, where you make a statement that says the transaction here, the output of this transaction, the amount that is created or transmitted, is less than or equal to the input, the amount that is consumed, meaning that it balances. You're not creating more money that went into it. You're not creating money out of nothing. So you can provide a proof that says the output is less than or equal to the inputs without revealing what the amount of the input or the output is. And that uses a branch of applied mathematics and cryptography called zero-knowledge proofs. The math is complex and outside of the scope here, but generally speaking, you're going to see something like that. ZK, zero-knowledge, is the prefix you see in many of these proofs. So you'll see things like ZK snark, ZK stark, etc., etc. These are different types of zero-knowledge proofs. You'll also hear names that describe with the word proof in them. For example, bulletproof is a type of range proof that's used in confidential transactions in Bitcoin, which again proves as a range proof that the outputs are less than or equal to the inputs. So you can have encrypted amounts where you can prove that you're not creating money out of thin air without actually revealing what the amount is. Zero knowledge proofs really are a fundamental building block of many of the privacy protecting and anonymity based currencies. There's a couple of questions about Polkadot. Both Iran and Bowl of Oatmeal in the chat are asking about Polkadot. Now, I don't know too much about Polkadot other than the basic concepts. But essentially, if you think of Ethereum as a programmable blockchain where you can write programs called smart contracts, Polkadot takes that one level further, and it is a programmable chain of chains, meaning that you can effectively program blockchains with their own consensus parameters and their currency and issuance schedule and the types of smart contracts they'll support, et cetera, within Polkadot that are essentially interoperable with each other. So it's a chain of chains. And the chains you create within Polkadot, as far as I remember, are called parachains. And there's a lot of new terminology introduced by this, but the basic idea is that you don't just design tokens, for example, like you do in Ethereum, or smart contracts and applications, but you can design and code entire blockchains with their own tokens and smart contracts within Polkadot. All right, 51% attacks on algorithmic stablecoins. Let's talk again about stablecoins, specifically algorithmic stablecoins. Daniel asks, do you think algorithmic stablecoins can ever be successful? And Daniel goes with an example of UST on the Luna network, which has amassed a significant market cap but is alleged to display Ponzi-like dynamics because it's not backed by anything other than the supply-demand of the UST-Luna pair. What is your opinion? Can a stablecoin be effectively administered in this way, or is it something to be avoided? So I don't know the details of UST on the Luna network, so I can't comment on that. Generally speaking, stablecoins change the set of risks that you face. Asset-backed stablecoins have counterparty risk, meaning that when you have an asset-backed stablecoin, the risk is that the asset that backs the stablecoin is on a traditional banking system, and therefore is subject to the rules of the traditional banking system, which means that those assets can be freezed and seized and stolen, hacked, removed, expropriated, embezzled by the owners of the stablecoin, et cetera, et cetera, et cetera. So you have the risks that are inherent in a blockchain, plus the risks that are inherent in a banking style asset, and all of the national geopolitical risks that come from operating in the international banking system. On a algorithmic stablecoin, you don't lose all of these risks or avoid them completely. You simply replace them with different risks, which may be better risks or worse risks depending on your risk appetite and how you evaluate these risks, what you're most concerned about. I am most familiar with the DAI stablecoin, the algorithmic stablecoin from MakerDAO. And DAI is an algorithmic stablecoin which is backed by cryptocurrency. So specifically by ETH or BAT or I believe a bunch of other cryptocurrencies, including some asset-backed stablecoins. So in the case of DAI, then the risks that you face are risks of the blockchain and the smart contract. So you have platform risks. What if there's a bug in the Ethereum virtual machine that hasn't been discovered yet? What if there's a problem with the consensus algorithm in Ethereum or something else that causes the platform itself to not function as expected? And we've seen some of these risks materialize when the gas fees have been so high that people can't actually recollateralize their DAI collateral, leading to liquidation of their DAI. So that's a classic platform risk, and this happened a couple years ago. On the other hand, you also have the risks, the software risks, the smart contract risk, which is what if there's a bug in the code that controls the issuance of DAI, the transfer of DAI, the ownership of DAI, or some of the secondary smart contracts that deal with the auctions for under-collateralized loans, etc., etc. And we've seen some of those risks materialize too. So you're substituting one set of risks for a different set of risks. You're substituting counterparty banking, freeze, seize, international monetary fund, geopolitical games from the banking system with software-based risks, risks in code and the platform. And perhaps those are risks that better fit your risk appetite. Maybe you would rather have blockchain risks than traditional banking risks. And for many people, that is the case. And so that's what we're dealing with algorithmic stablecoins. I think algorithmic stablecoins have already demonstrated that they can be quite successful in maintaining the peg more often than not. And where they have the main problem that algorithmic stablecoins have is the platform risks and what happens when things in the platform go outside of the normal behavior, for example, with fees. So as a follow-up question, Michael asks, how can DAI remain stable when the underlying assets face high volatility? Well, it's really interesting to examine that, and I encourage you to read more about algorithmic stablecoins and specifically DAI to understand how that works. But the bottom line is that you put collateral, for example, ETH, into a contract, and you are issued a certain amount of DAI. And you have to have more than 100% collateralization. So let's say I put in, and I'm going to use dollar equivalent values just to make things clearer. Let's say I put in $1,000 worth of ETH, and then I can take out, let's say, $800 worth of DAI. And that way, there's a reserve. Like, I'm not taking out as much as I put in, meaning that my my DAI loan is over collateralized, and that's one of the fundamental concepts in algorithmic stablecoins. Now, if the value of ETH drops, as it drops, and my ETH is worth, let's say, less than 1,000, is worth 900, and I've taken out 800 in DAI, now the ratio of over-collateralization that I have has reduced. At some point, when it drops below a certain point, I become at risk of liquidation. And so what happens is I then need to do one of two things. Either put some of the DAI back into the contract, so reduce the amount I've taken out. So let's say I've taken out 800 DAI, I put 200 back in. Now I only have 600 DAI that I've taken out of the contract that I've used. I return some of that loan effectively, and that adjusts my collateralization ratio. Or I put more collateral in to shore up the collateralization. And those are the two options I have. Now, if I don't do anything, at some point I reach a collateralization ratio that is no longer viable, and then what happens is automatically my collateralized DAI loan will basically be auctioned. And that means that the collateral I've put in, the reserve, is sold on a secondary market to try to recover the value of that ETH before it drops too much. and I lose my reserve. I lose the collateral that I've put in. I still obviously have the DAI, but because that will happen before the value of the ETH gets to the point where it's equal, 1-to-1 collateralization ratio, effectively I'm going to lose some value, perhaps a significant value of that ETH. Panos asks, what is your opinion about the use of homomorphic cryptography in cryptocurrencies and relevant platforms? Are there any interesting projects we should keep an eye on? Honestly, I find the two research areas of zero-knowledge proofs and homomorphic encryption that together are the backbone of a lot of the anonymity, privacy, but also optimization and scalability projects that we see in the space. Those two research areas have absolutely exploded in the last 5 to 10 years, especially in the last 5, and have progressed with leaps and bounds. So it's like a golden age, if you like, of zero-knowledge proofs and homomorphic cryptography, and as part of the broader global golden age of cryptography that came from the applied use of cryptography in cryptocurrencies. So because these cryptocurrencies are creating practical applications that generate essentially money for this research, and companies have the incentive to fund this research because it can turn into projects that generate a lot of money for these companies. We're seeing a lot of research happening, and a lot of funded research happening, and a lot of research results coming out of that. What interesting projects should we keep an eye on? It's hard to really focus, but I think zero-knowledge proofs are kind of the more important technology compared to the more narrower area of homomorphic cryptography. So homomorphic cryptography can be used in zero-knowledge proofs, and it's a broader area that does other things as well. Paul asks about the risk of holding Tether, USDT. Can you provide more information on the recent controversy surrounding Tether, that it has made statements about the stablecoins being fully backed by fiat currencies? Is there a risk to holding USDT? Honestly, since the very beginning of Tether, there have been rumors, accusations, controversy surrounding it. It's a controversial stablecoin. And so I don't really comment on these controversies. What I'll do is talk about the more general problem, which is with any stablecoin that it has assets that back it, you have to do a lot of work if you're the stablecoin owner or operator, if you like, to prove that your stablecoin is indeed fully backed, 100% backed. It's not enough to show that you have the reserves. It's not enough to show that you have the assets. And the reason it's not enough is because you could have the assets in the bank, but maybe that bank has already issued loans for those assets outside of your stablecoin. So you say that these assets are backing your stablecoin, but to the bank you've said these assets also back this other loan. Maybe you use it as a real estate investment, or you get some other collateralized loan. You've basically rehypothecated or under-collateralized your stablecoin. The money that's in the bank is spoken for twice. It's backing the stablecoin theoretically, but it's also backing some other liability that you haven't talked about to your investors and users. So in order to do a full accounting of a stablecoin and show that it's 100% backed, you have to do a full in-depth audit of both assets and liabilities for the entire system that that stablecoin is based on. And that's a very high burden. And in fact, if you think about it, that burden of doing an audit of the existence of your reserve and the degree of collateralization that you have of your reserve is the banking system. That is the oversight framework of the national bank charters. That's what a bank has to do. And even banks don't do that very well. And every now and then you have bank crises because the banks, turns out, made risky loans, or had cooked the books, or their accounting wasn't good, or whatever else may have happened. So you need something at least as good as the various national bank charter and bank oversight and audit mechanisms to run a stablecoin, which is why many regulators are trying to regulate stablecoins the same way that you regulate the banking system, and see it as a systemic threat to the banking system and the broader economy. So there are definitely risks. Those risks are not specific to Tether. They are risks that exist in anything that has assets backing it, supposedly. Ridwan asks, can I elaborate on Polkadot's consensus mechanism, which is called Grandpa? It's the ghost-based, which is, ghost is the heaviest object state tree or something like that, which is a mechanism used in the consensus algorithm of Ethereum at first, and other systems too. Grandpa is kind of an extension of that, the recursive ancestor deriving prefix agreement, and Babe, the blind assignments for blockchain extension. I do not know how those work. So I can't really tell you much about that consensus algorithm. I know it's one of the areas that Polkadot has introduced as an innovation, and I haven't personally studied it enough to understand how it works. And I don't know if it's used any more broadly than Polkadot. So I'm afraid I can't answer your question at this time, but certainly encourage you to seek more information and research and study that if that's something that interests you. Maybe you could come back and explain it to the rest of us. That would be a great exercise. We also have a question on colored coins, which I'll address very, very quickly before we move on to other topics. Adrian asks, in the presentation, colored coins are mentioned, but I can't find any reference in the PowerPoint about colored coins. Can you provide a short explanation to understand and differentiate them? I think the best way I can explain this is colored coins are a legacy obsolete system that was initially proposed for and implemented in Bitcoin in order to implement what we today call tokens. So everything that we use tokens for today, whether that's tokens that represent securities, tokens that are used for access control, tokens that represent fungible or non-fungible deeds to different types of assets, all of the uses, what we used to call tokens, were initially conceived as colored coins. And the idea of a colored coin is that you take a minuscule amount of a coin. In Bitcoin, for example, you take a Satoshi, and then you add some metadata to that Satoshi that you use applications to carry forward as that Satoshi is traded, so that the Satoshi means something more than just its value in Bitcoin, which is very, very low, 1 Satoshi. This is a bit like taking a dollar bill and stamping on it, this is 1 share of IBM, or this is 1 share of Microsoft, or this gives you access to the Lady Gaga concert. And then that's stamped with some kind of official certificate. And so it's still a dollar bill. If you wanted to, you could spend it as a dollar bill, but that value is low, whereas its value as, let's say, a Lady Gaga concert ticket is much higher. So it acts more as a token of the metadata that it carries than its face value as a currency unit. So that's what colored coins are. They were attempts to add metadata to small amounts of cryptocurrency, specifically Satoshis or hundreds of Satoshis, so as to implement some form of tokens. Once Ethereum came on the scene and created a much more standardized, flexible mechanism for creating both fungible and non-fungible tokens, nobody wanted to do colored coins anymore. And people still keep trying to do tokens and colored coins and NFTs on Bitcoin. I have repeatedly said why I think that's a waste of time and effort, and why that's precisely a good use for the Ethereum platform and what it was actually designed to do. So colored coins, obsolete technology. And we do all of these things with tokens nowadays. All right, let me take a brief second and go through the chat and see if you have any other follow-up questions. All right. Ashwin asks about Monero, privacy coin. In the notes, we have a reference statement that says that Monero hides transaction history by associating its transaction input to not just one, but many possibly equally valid outputs. Unlike Bitcoin, where the outputs are each related to the inputs, how and which transaction inputs will be selected? And what about the other outputs of a ring size? So this really refers to what are called ring signatures, which is a way that Monero uses to obfuscate the relationship between outputs and inputs by essentially inviting other participants into the ring who are not really parties to the transaction, but appear to be parties to the transaction. So you can't see which inputs are actually being spent and which outputs relate to that. It breaks the statistical analysis. So I can't really elaborate much more than that. I understand it on a very superficial level of how Monero's ring signatures work. But it's a commonly used anonymity strategy, and it's not unlike a coin join, only the difference is in a coin join all of the inputs and all of the outputs are actually used. You just have so many that you obfuscate their relationships. Whereas the nice thing about Monero is that you have participants in the ring signature, from what I understand, who are not actually participating in the ring signature. And that makes it really impossible to do this statistical analysis, or at least it increases the so-called anonymity set. So when we talk about anonymity coins, one of the key characteristics of an anonymity or privacy technology in general is the anonymity set. Think of it this way: if you're trying to hide in a crowd, how big is the crowd that you can hide in? So the bigger the crowd, the more people who are participating in the anonymity set, the harder it is to draw conclusions from merely the fact that you're participating in this anonymity set. Hani has some questions about the relationship between blockchains, cryptocurrencies, native currencies. I'd like to know about dApps that use the Ethereum network. Do they have a blockchain for themselves or work on Ethereum? For example, EOS has a blockchain for itself, but it uses Ethereum instead of its native currency. A bit confused here. Can a blockchain work inside a bigger blockchain? Generally speaking, with the exception of a platform designed to do that like Polkadot, no. However, one thing that we've seen repeatedly is that platforms, blockchains that support smart contracts such as Ethereum, and have the ability to have tokens, can very easily create tokens that represent currencies from other blockchains. For example, in Ethereum, you can have wrapped Bitcoin or even wrapped Ethereum, which is basically an ERC20 token that represents an amount of Bitcoin. And you can exchange Bitcoin for wrapped Bitcoin, and sometimes you can do these exchanges between two blockchains using a so-called atomic swap, which is a decentralized mechanism for swapping, locking one amount of currency in one blockchain and unlocking it in the other, so that the two are effectively connected. And that's where you'll see what appears to be a foreign currency, a currency that comes from another blockchain, being used in the smart contracts and applications of a blockchain instead of the native currency. For the most part, that's using the token capability, the tokenization capability. And I believe that's also what's happening in the example that you have, where EOS can use Ether inside EOS smart contracts. I may be wrong about that, but that's my understanding. Dina has a question about privacy coins. Why was Bitcoin not designed as a privacy coin to increase anonymity on the network? That is a great question, and I don't have the answer to that. In fact, I think that is one of the biggest design flaws of Bitcoin, is that it didn't have sufficient privacy, and still doesn't have sufficient privacy, but it didn't have it baked in from the design. And then as it became more and more difficult to introduce changes to the Bitcoin system, because it requires overwhelming consensus, that's one of the areas that becomes a weakness for Bitcoin over the long term. Now, for some people, not having privacy is a strength. You see, the argument goes that if Bitcoin had strong privacy, it would have been attacked more vigorously by governments and regulators. And because it lacks privacy, it's more friendly to regulators and law enforcement. I don't know if that's true. I think it's besides the point. I don't think there's much point of having a digital currency with reduced privacy to appeal to regulators. Although, in fact, that's the kind of design principle of Ripple, regulator-friendly digital currencies. To me, I think that's a waste of time, but that's my personal opinion. I'm baffled as to why there wasn't stronger privacy. Although one of the reasons possibly is that a lot of the anonymity and privacy protecting technologies that have been developed since are much better at doing anonymity and privacy through zero-knowledge proofs, for example, things like ring signatures, efficiently. Back when Bitcoin was originally designed, it was actually very difficult to do that stuff efficiently, meaning that you would end up with transactions that are 10K in size, so 20 times greater in size or 30 times greater in size than the size transactions actually have. So there was a design trade-off between scalability and privacy in the early days. And that might have been one of the reasons why Satoshi Nakamoto didn't include more privacy capabilities or technologies early on in Bitcoin. And unfortunately, it's become harder and harder to introduce new features to that. Dina asks, can you elaborate on side chains and parachains or parallel chains? How do they operate? You know, the problem here is that these terms do not have clear definitions. The original term sidechain was the idea that you have a chain that runs to the side of an established blockchain like Bitcoin. It's a separate blockchain, but you have the ability to do a two-way peg where you can transfer currency from one chain to the other and back and forth. A classic example of that would be the Liquid sidechain that allows you to take Bitcoin and convert it to liquid Bitcoin and then convert it back to Bitcoin when you want. The idea being that you can effectively experiment on a different blockchain with features and consensus algorithms and other capabilities more freely than you can on the main chain. Now, since then, people have proposed a number of different mechanisms that implement sidechains of different styles, including things like drive chains, state chains, parachains, etc. And while those all sound similar to a sidechain, they may be completely different in the way they work and involve completely different concepts. So it's not really useful to use those words to get a classification, and you have to be specific about which one you're talking about. So the parachains technology in Polkadot is very, very different from, let's say, drive chains or state chains. So I'd have to be looking at a specific one, but generally speaking, all of these things are a chain, so there's an additional chain of some kind, and they relate to another chain through some kind of mechanism that allows you to move back and forth, either move value or sometimes move other forms of state, like tokens, between the various chains. Marcel asks, can you explain the way Chainlink wants to connect off-chain data to the blockchain and make it on-chain data? My understanding of Chainlink is limited. Again, I'm going to put that little disclaimer. This is a very broad space, so it's difficult to catch up with everything. But what I understand is that Chainlink is attempting to solve the so-called Oracle problem. The Oracle problem is that smart contracts, when they operate within the consensus rules of a blockchain, can only refer to data that is on the blockchain. And that's because they have to have deterministic execution. You have to have the ability to arrive at the same results, the same conclusions, for everyone validating the execution of a smart contract. So if I run something on an Ethereum smart contract, every node on the Ethereum network validating that transaction needs to get the same result. And the way deterministic execution is achieved is by ensuring that the only data that the smart contract can refer to is the stuff that's on the blockchain that is under the same consensus rules. The Oracle problem is that very often there is information in the real world, information such as weather data, temperature data, stock data, pricing data, like how much is Ethereum worth at the moment, which is useful in the context of a smart contract, but it's difficult to find a way to refer to that external data in a way that's also deterministic. So that if, for example, you want a smart contract that does something based on the price of Ethereum on exchanges, on markets worldwide, that information isn't in the blockchain, in the Ethereum blockchain. So you have to introduce it somehow. And then you have to introduce it in a way that the smart contract runs the same for everybody, because what it thinks, what one node thinks is the price of Ethereum is the same as what another node thinks is the price of Ethereum at the same time. An easy way to solve the Oracle problem, of course, is to centralize it. So if you simply post that value from a centralized source to the smart contract, problem solved. The smart contract always refers the same value. However, then you've sacrificed decentralization. So what happens if that central party is coerced into posting the wrong price for Ethereum? Now you can imagine this has broad-ranging implications. Let's say you have a smart contract that underpins a stablecoin like DAI, and how much collateral you have to have in your contracts depends on the price of Ethereum. And so how do you trust that the price of Ethereum that's going to be used is correct and that no one can be coerced or hacked into posting an incorrect price? Generally speaking, those problems are solved by decentralizing the data so that it takes more than one person to feed the price of Ethereum to the smart contract. But then that makes it difficult to have deterministic computation. That's the problem that Chainlink is attempting to solve. As far as I understand it, Chainlink is intended to be an oracle-based chain that uses a decentralized oracle system in order to feed information into the blockchain in a decentralized manner, but at the same time one that allows you to do deterministic computation of values. Hopefully that helps. I'm not entirely sure that I expressed it well, but that's the best I could do. All right, the next question comes from Bradley, and it's about delegated proof of stake. Bradley says, while researching the delegated proof of stake model, it appears that one of the biggest drawbacks is that it is sacrificing decentralization for scalability. For example, Ethereum's founder, Vitalik Buterin, suggested that DPoS may be conducive for voter bribery and creating voting cartels. Are the downsides to DPoS outweighing the positives? Well, Bradley, it depends. I think it's an accurate statement that delegated proof of stake involves some compromise of decentralization in order to improve scalability. And this is because decentralization and scalability are part of what's known as the blockchain trilemma, where you have to sacrifice one of the three capabilities or features of your blockchain. So you have decentralization, you have scalability, and you have security. And so you have to choose any two. It can be decentralized and secure but not scalable. It can be scalable and decentralized but not secure. It can be secure and scalable but not decentralized, etc., etc. So that's generally what we describe when we're talking about a trilemma. So it's I think fair to argue that DPoS makes that trade-off. Now, the real question is that trade-off a drawback? Is that a downside? And are the downsides to DPoS outweighing the positives that you ask in your paragraph? And the problem with that question is that there's no one answer. It depends on what you're trying to achieve with the blockchain, what you're trying to achieve with the platform. And I think this goes for all of the design trade-offs. If you don't care about decentralization because the application model you have doesn't need decentralization, then this is a very reasonable trade-off. In fact, if scalability is more important to you. Imagine, for example, that what you're trying to do is run this in an environment where you have an effective cartel already, where you have a federated consensus model. So does sacrificing decentralization and creating the potential of a voting cartel worry you when you already have a voting cartel? Let's say you wanted to have a market for trading, I don't know, Russian rubles between 5 of the largest Russian banks. Does it matter? You already have a voting cartel. It's a closed system with a federated consensus algorithm between those 5 parties. So are you really losing anything by using a delegated proof of stake system? No. So whether it's a drawback or an advantage depends on what application you're trying to do and what capabilities that application requires. And that will color your assessment of this technology. For those for whom decentralization is important, immediately you would look at this and say, this is a drawback. I'm not willing to sacrifice that in order to achieve scalability. I'd rather sacrifice something else in order to achieve scalability, or sacrifice scalability itself to achieve decentralization. So you do the opposite trade-off. And so there is no absolute or objective answer to which is the best way to design the trade-offs that are involved in these blockchains. This is a really, really important point to understand, because very often you're going to hear a lot of people in this industry who describe these design trade-offs as obvious objective truth or value and say, clearly, decentralization is more important than scalability. Clearly, scalability is more important than decentralization. Or they hide the trade-off. They'll say, well, we achieved scalability and we haven't sacrificed any decentralization, which is unlikely. So in all of these cases, when you hear someone describing a specific design trade-off as either an advantage or a drawback, what they're doing is they're revealing to you the foundational assumptions that they've made about the values or the use cases that they consider important. They're telling you, this is the filter through which I evaluate blockchains, and my filter is all about scalability, or my filter is all about decentralization, or censorship resistance, or robust execution, or monetary supply auditability, or whatever. And if that is the most important thing to them, then everything else is evaluated based on whether it delivers that. If, however, that is not the most important thing to you, then no matter how many times they tell you this is an advantage, it's not, because it's not to you. There is no absolute framework that is the same for everyone. Despite the fact that maximalists in every single part of our industry will tell you that there is an objective value moral framework under which everything should be evaluated, and anybody who tells you that that is not the objective moral value framework is a scammer, a shill, a traitor, a communist, a fascist, or whatever. Everything here has to do with what are you trying to achieve. If you look at this purely from the perspective of technology, then none of the questions about which system is best have an answer unless you say first what application you want to evaluate it against. And the same thing goes for example, delegated proof of stake. All right, some additional questions about different platforms and coins. KF Chan asks, what is the benefit of having a 10-minute block time in Bitcoin? What if Satoshi had set the difficulty to average 5 minutes? What would the consequences be? We actually know the answer to this because this is something that Satoshi discussed while Satoshi was around. So, Satoshi experimented with different block times, and one of the things that happens when you have a 10-minute block time in the current environment of Bitcoin, for example, is what is known as a consensus fork. This is where two miners that are on different parts of the network that from a network perspective topologically are far from each other, find the solution to the proof of work algorithm for their respective candidate blocks more or less at the same time, within a few seconds of each other, or at most within 10 seconds of each other. And they each announce that block and propagate it across the network. And as it travels across the network, half of the network thinks that this is the winning block with the longest chain, and the other half of the network thinks that this is the winning block of the longest chain. And you have a consensus fork where for a period of one block, possibly two, possibly three, you have a conflicting chain. Now, usually this gets resolved immediately because the very next block is found either by those extending this chain or by those extending that chain, and then that becomes longer and the other one gets forgotten and goes away. And you have a reorganization of the duplicate block. Effectively, all of its transactions are checked against the new blocks, and if they already exist, they're discarded. If they don't, they go back in the mempool and wait for another chance. Now, consensus forks happen on average every couple of weeks in Bitcoin. They're perfectly normal, and they get resolved within one block. In fact, if you look in the Bitcoin white paper, there is one mathematical formula, and that mathematical formula estimates the probability of a consensus fork of length n. So what is the probability of a 1 block, 2 block, 3 block fork expressed as a function of n? And the probability decreases exponentially such that at the point of 6 blocks, the possibility that you have a consensus fork that's 6 blocks long is vanishingly small, and that's why we set the standard at 6 blocks. For this is so confirmed that it will not get rewritten. This does not happen statistically. All right, so that's a probabilistic system of consensus. Now, this very much depends on the timing. If you had blocks coming up more often than 10 minutes, if you had, for example, blocks coming up every 5 minutes, the probability of a 1 block consensus fork happening doubles. So you now have twice as many normal consensus forks happening. So maybe instead of once every 2 weeks, you have it once a week, or even a bit more often on average. You have consensus forks, and so on and so forth. Now, if one of the other problems you have here is that in Bitcoin's consensus algorithm, the winner takes all, and the other miner who found a block that eventually got orphaned or excluded from the chain is a better term, will not earn anything. They get nothing for coming in second place, even if for 1 block they thought they were in first place. And not all consensus algorithms work that way. We talked briefly earlier about Ghost, the greedy heaviest objects that and in the Ghost consensus algorithm that's used in Ethereum, it's not just the winner takes all, but you have this concept of uncles, which are blocks that eventually ended up on their own chain. They don't have any children of their own. They were not extended, but they still earn some of the reward. And that allows Ethereum to have much smaller time frames in the order of about 15 seconds between blocks. And it's going to have many, many more simultaneous discoveries of blocks across the network by miners in its proof of work algorithm. But those other blocks will also share part of the reward, and they will not get discarded. So it's a trade-off. And the 10-minute mark seemed to Satoshi to be a good balance between it gets confirmed fast enough, but we don't have too many consensus forks as we would if we had it more frequent. And that's how Satoshi picked it. And Andreas asks a follow-up. What happens to transactions that were included in the second place conflicting block, the childless block? People often call these orphan blocks, but they're not orphans. They're childless. They are, and that's why in Ethereum they're called uncles, because they don't have children. They have a parent. They have the same parent as the other block that won. They just don't have children because nobody ends up extending them. And so what happens to those transactions? Let me be clear. Let me play this out for you in a bit more detail so you can understand it. Let's say you're on, as I said, there's 2 parts of the network. This part thinks that block A won. This part thinks that block B won. And then we have a child for block A that resolves the question, which means that block A is now extended with a child. Its child is called Bob. And so this chain ends up getting longer, which means that this chain, which had block B in it, has now been left without a child, and it's not as long as the A block chain, and so as a result, this block will get dropped. Now, all of the nodes on this side of the network that thought that this had won have already taken the transactions that were confirmed in this block out of the mempool and considered them confirmed. And now they discover they're wrong about that assessment, because that block was not in fact on the longest chain. So what do? They trim it. They take all of its transactions. They now have a copy of the other chain, which has the A block. And in practice, the A and B blocks that ended up being found more or less at the same time will share more than 90% of the transactions. And that's because when the miners are creating candidate blocks and they're pulling block transactions from the mempool, and they're trying to pick the transactions with the most transaction fees, the most profitable transaction from the mempool, it's likely that they're going to see more or less the same transactions. If they've constructed their mempool and they're as well connected to the Bitcoin network, the top most profitable transactions in the mempool are going to be more or less the same. I say more or less because they're not exactly the same. Maybe they didn't arrive in the same order. Maybe one of them has been delayed or lost or hasn't been seen by the other miner. So there's an overlap. Let's say 95%. Let's say 99% to be more accurate. So out of 2,000 transactions, maybe 1,980 transactions are the same, and then there's 20 transactions that are different between A and B. So when this block gets discarded, out of the, say, 2,000 transactions that it contains, the nodes will see that, let's say, 1,980 were confirmed in the A block anyway. So those transactions are good. They also did get confirmed. And then there's just the 20 transactions or so that were in this block that's going to get discarded that were not confirmed in the A block. And maybe those got confirmed in A's child because they arrived a bit later and they got put in the next block, in which case, great. And if they weren't confirmed in A or its child, then they go back in the mempool to wait for their turn. So it's effectively a process of reconciliation. I hope that helps. All right, another question about smart contracts. This is not from this week's topics, but I think it's useful and it covers some of the things we talked about the other day. Actually, that's a good follow-up question in the chat, so I'm going to quickly go in it. Can there be a paternity test protocol for child ownership in the blockchain? I don't know if you meant that as a joke, but let me explain very quickly why there is in fact such a thing. Every block in Bitcoin contains in its header the parent block hash. And it is that previous block or parent block hash that allows the blocks to form a chain. So every child has in it the hash of its parent. When miners create a new child, they have to specify in that child who its parent was, which chain they're extending, which one they're giving a child to. They have to put the paternity in the form of a hash, a fingerprint of the parent, in the child to ensure that there's a link from the child to the parent to the grandparent all the way back to the genesis block. That's why we call it a block chain. They are chained together specifically by this paternity fingerprint that is in every block. So every block identifies its child. And then when the miners try to find the solutions of proof of work algorithm, they're committing to that parent designation in that child because that's part of what makes up the hash of the child. So the hash of the child is affected by the hash of the parent, which is why if you try to change the past, you then have to recalculate all of the blocks further down, because if the parent changes, then the child changes, then the grandchild changes, and so on and so forth. These changes ripple forward because the hashes depend on each other. So whether you were asking that as a joke or not, I think it's a good question, and I answered it anyway. I hope that helps. Farad asks, unlike Bitcoin that has a 21 million coin limit, Ethereum has no supply limit. Do you think that is a negative for Ethereum despite its anticipated move to the proof of stake later this year? Is it a negative or is it a positive? I will refer you back to the thing I spent a good 10 minutes describing, which is there are no absolute value judgments in the relative trade-offs between the different coins. If you want to use Ethereum as sound money, it's obviously a negative. If you want to use it as a flexible dApp platform, then you don't care about monetary policy. Perhaps you don't, perhaps you do. That's something that you have to tell me what you care about, so I can tell you if it's a negative or a positive. Because it is a trade-off. Not having a fixed monetary supply gives Ethereum a degree of flexibility. The argument on the Ethereum side is that that degree of flexibility is part of what allows it to do what it does best as a platform. And if you say that to a Bitcoin maximalist, their hair catches fire and they say, clearly you are not seeing the value that I see. They won't say it as politely as that. And the answer is yes, we're not seeing the same value if I was to take the Ethereum perspective. And if I was to take the Bitcoin perspective and someone in Ethereum said sound money doesn't matter, I would say, well, yes, but to me it does. And we're not seeing the same value. Answering this question tells someone what you value, and it doesn't tell anyone whether Ethereum and Bitcoin is better for them, but it does tell them what you value. So you answer this question, and that will reveal something about what you find important in these trade-offs. Iman asks, can a smart contract be developed to run for many, many years? Like, for example, in a use case of a police department to register car accidents, and each car accident, it is called and executed. So, forget the use case. I'm not quite sure that, and again, with every use case, I will ask you the burning question, why do you need a blockchain for that? Who's trying to censor car accident information? Maybe in some countries there is so much corruption that police records are compromised and vulnerable to corruption. But in any case, that's why do you need a blockchain for that is a separate conversation. But let's assume you do need a blockchain for that. It's important to understand how smart contracts work. Smart contracts do not run all the time. Smart contracts only run when a transaction is created and mined that, or confirmed, if you like, that calls on that smart contract. So, if in your example, every car accident is a transaction that someone does and pays the fees, and that transaction calls the car accident register or smart contract, it will run that smart contract. That smart contract will run in order to process that transaction, and that's when it runs, once, when that transaction is processed. That's what it means to have a transaction in a smart contract blockchain. It means to execute that transaction smart contract, the smart contract that it is calling. And the transaction will say, call this smart contract and pass this data. And in order to validate that that transaction is correct or valid, you have to run the smart contract at that address. So the smart contract doesn't run all the time. In fact, you can't automatically run a smart contract on its own. Smart contracts only run in the context of the transaction that calls them. So transactions happen which call smart contracts. Smart contracts do not run spontaneously, and they do not run outside of the context of a transaction. They only run within the context of a transaction. And as such, they are always available. Every contract that exists in a smart contract platform is still available. Once it's been registered, from that point on, it is available for any transaction to call it or any other contract to call it. It always starts with a transaction. And this is something that is often missed and one of the more important things to explain about smart contract platforms. It always starts with a transaction. Okay, if you remember that rule, it will help you understand smart contracts much better. It changes the way you program. Obviously, if you're writing a program for your desktop or a mobile phone, you can cause that program to run when you boot the computer. You can cause it to run when an event happens, like you turn on Bluetooth or your GPS location changes or whatever, or it can run in the background all the time. Those contexts, those execution or runtime contexts, as we would call them in programming, don't make sense in a smart contract environment. In a smart contract environment, the execution context is the transaction. So it always starts with a transaction. And what that means is if you want a contract to run periodically, what we would call a cron job or a scheduled job in an operating system context, what you have to do actually is generate transactions periodically that call the smart contract, which is something that you would do outside of the blockchain. You can't make in the blockchain a smart contract that spontaneously runs or starts running or that continuously runs outside of the context of a transaction. And thank you for that question, Iman, because I think it helps to illuminate one of the things that is confusing about smart contracts, especially for programmers who are used to working in the context of an operating system or some other embedded device, understanding how and when smart contracts execute. Infinite asks, concerning blockchains handling data storage, where is the decentralized data actually stored? I can only imagine miners providing their hard drives, but wouldn't this allow for deletion? This is a great question, and it's a question that has been answered many different ways in many different systems. For the most part, when you have things like Filecoin or storage coin, IPFS, and the many, many other protocols that have emerged around decentralized files, how it actually works is really one of the key design features that you need to consider as to whether this is a good way to do it for your particular application. Generally speaking, the data is not usually stored on the blockchain. It is stored using some kind of decentralized file storage. What that means, usually what that means, is very similar to the technologies used in file sharing and things like BitTorrent in the past. Usually those involve what's called a decentralized or distributed hash table, a DHT. Or some other form of content addressable storage, CAS. What that means is you have a piece of data. That piece of data has a checksum or fingerprint, a hash, and that hash becomes a unique identifier that allows you to identify that particular item of data. And that's called a content addressable storage. So every piece of content has its own address, and that address allows you to retrieve it, even if it's stored in a decentralized manner. Furthermore, the data itself may be broken into chunks. For example, a file is broken into smaller pieces, and then those pieces may be spread out and decentralized or distributed across a distributed file system. So in BitTorrent, that used to be called blocks or chunks in other file sharing protocols that existed. So these blocks and chunks, again, they have a fingerprint, and you have a table that says which file they belong to, again, by fingerprint or hash. And as long as the chunks exist, and usually a chunk is stored more than once in more than one computer, then as long as you can retrieve one copy of each of the chunks that make up the file, you can put together the file again. And the way that's done in a decentralized file system is that different chunks of the file are stored on different computers, and there's more than one copy of each chunk, so that if somebody's computer goes away or disappears, somebody else has those chunks too, and as long as there are enough copies where you can pull all of the different chunks together, you can recreate the file. If there are not enough copies, then that file effectively is no longer stored on the decentralized file system. And that may happen over time if something isn't used. There's also a concept of caching, meaning that the more popular or more frequently a specific piece of content or file is accessed, the more copies of it will be stored on more computers. So for example, if you access a file, maybe you keep all of it or some of its chunks around to help others access it, and that way the more a file is accessed and wanted, the more chunks and copies of chunks of it exist in more places, etc., etc. So that's how the decentralized files are stored to ensure that there's always some copy available of the things that are really popular. Now, in addition to that, there's very often this storage is part of how the consensus algorithm works. So for example, there are consensus algorithms that depend on you having things in storage, the so-called proof of storage models. And in these models, you have some data, whether it's these decentralized files or whether it's deterministic random data, data generated from the repeated application of hash functions or some other random number generator, where the system will ask you to prove that you have the data by asking for a specific byte of a specific location, and you fulfill the consensus algorithm by returning that value and proving that you actually still have a copy of that data. And because it's very expensive to generate it, but inexpensive to store it, you generate it once, you store it, and then when it's asked for, you show that you have it. So unlike proof of work, where the difficult part is generating the data in real time, with proof of storage, you generate it once, and then you store large amounts of data, very large amounts of data, to prove that you have the storage to back the system. Asim asks, so we don't store data on the blockchain, we just use it to check the data integrity and authenticity? Yes, because the blockchain itself has to be replicated in its entirety everywhere, and therefore that's an inefficient way of storing data. Because you don't need to have 50,000 copies of the file, you just need one. And to be sure, you need 1.5, 2, 3 to retrieve any file. You certainly don't need 50,000. So, for example, the Bitcoin blockchain exists in 50,000 copies. Why would you want every file that's relevant to that blockchain to be stored in 50,000 copies when you only need one, really, to resurrect it on the network. So for efficiency reasons, we store the fingerprints because what we care about is the integrity. We need to ensure that what we reconstructed is the original file, but we don't store the data itself. And I believe that's all of the questions we had from the forums. Let me just very quickly check in the chat and see if there's anything else. All right, I'll do one quick question. It's from an earlier week. It's really more week 2 or 3, but I'll answer it anyway. M-Chain asks, if I buy Bitcoin and store it on a hardware wallet, do I need to make regular checks on the wallet, or can I forget about it and use the Bitcoin after 20 years? Bottom line, M-Chain, is, first of all, the Bitcoin isn't on the hardware wallet. The Bitcoin is on the blockchain. And if you've made a backup of your keys in the form of your mnemonic phrase or seed phrase, the 12 English words, you don't even need to have it on a hardware wallet. In fact, it's not safe to stay that long on a hardware wallet that you haven't touched. And here's why. Hardware wallets involve a physical implementation of key storage and security, bits of silicon and firmware and software written on this device that ensures that you can only open it if you have the correct PIN, etc., etc. That means that that device may have vulnerabilities to physical direct access, meaning that if someone comes and steals that device from you, and that device has a vulnerability, they may be able to extract the keys from that device, which is why if I have Bitcoin stored on the Bitcoin blockchain on keys that I generated on a hardware wallet, and I keep those keys on that hardware wallet as well as the backup, of course, but I keep the hardware wallet because I use it from time to time, then I will want to continuously maintain that hardware wallet by doing firmware updates to fix any security problems that may have been discovered. So let's say I have my Ledger or Trezor hardware wallet and I use it, then I would want to do updates. If I'm not doing updates on that device, then I'm not going to leave the keys on that device. What I'll do is I'll wipe the device. Now the keys only exist as my 12-word phrase that I've etched on steel. Steel doesn't require firmware upgrades. Really cool trick. And so my Bitcoin is sitting on the blockchain. My keys are secure because I have my backup. I've etched it on steel. I've got my crypto steel capsule or something, or just a very simple mechanical device where I've etched the words on steel. So I know I can get my keys back. The hardware wallet itself I wipe. And maybe I keep it, and then 20 years from now, I decide I want to use my Bitcoin. I'll take that hardware wallet. I will first upgrade its firmware all the way up to today, and then I will recover the keys onto the hardware wallet by typing in those 12 words onto the hardware wallet, if that makes sense, because then I actually want to use it. The hardware wallet isn't for storing the keys. It's for generating the keys and signing transactions when you need them. The actual storage of the keys is in the 12 words that you back up. And I wouldn't use a hardware wallet for long-term unattended storage because it's vulnerable. Now, of course, you say, well, so are the 12 words that I've etched on steel. Yes, and you need to physically protect them from someone having access to them. You know, there's no reason to leave it on a hardware wallet. But if you have, to answer the broader question, if you have Bitcoin on the blockchain that you put with keys that you created 20 years ago, I would put a very high probability that you can still access and use and spend that Bitcoin 20 years later. And the reason for that is because the developers and the community and the consensus rules in Bitcoin, specifically in Bitcoin, are, as a culture, as a set of principles, very careful to never make changes that invalidate the value or use or keys of the past. None of the changes made to Bitcoin break a Bitcoin address that was in the first block. None of them. And that's on purpose. Never will you see a change accepted, in my opinion, based on the community culture that I've seen, that will invalidate your holding of Bitcoin because you didn't do something, upgrade, refresh, move, whatever. There's a lot of resistance to forcing Bitcoin owners to have to take a positive action to maintain their wealth. You should be able to preserve your wealth without doing anything, and that's on principle. And part of the principle is that for many people who are in Bitcoin, maybe those keys are, buried, either literally or figuratively. They're very inaccessible, and it's a very big burden to go, and a very big risk to go and resurrect the keys and restore them and move them or do a transaction or do something with those keys just to preserve the value that you already had. So on principle, those types of changes are not acceptable in the Bitcoin community, which means that Satoshi can still use the keys from block 1. You will still be able to use the keys in 20 years. I'm very confident. Without having touched them at all in the meantime. And that's everything. Went 3 minutes over. Thank you so much for joining me today. This is week 7. This is my last week. Next week is Professor Polemitis, I believe, who will be taking you through week 8. Thank you so much for attending this, the 17th semester of the Massive Open Online course for the Master's degree in Digital Currencies by the University of Nicosia. My name is Andreas. I'm Antonopoulos. I've been your teacher for this session, and it has been an absolute pleasure answering your questions. Thank you so much for giving me your time and attention. And hopefully I'll see you next semester. Take care, everyone. Bye-bye.